The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you, Scott. Well, good morning, and I'm really pleased to be here today and present you on a topic that I have been working now for some time, and I will show you this within permissible moment redistribution limits, and I'm going to use this in the context of experimental and advanced FEM analysis using abacus. So the objectives of our research was to provide permissible moment redistribution limits for continuous fiber-reinforced polymers, strengthened reinforced concrete beams. Some of the outcomes from this research was that we were actually able to provide some redistribution limits, provided that the curvature ductility capacity of a section, for example, is 3.5, and that's the moment redistribution limit. Until recently, moment redistribution limits were not included or considered in the retrofit applications. And the reason why is because of these issues. The behavior of FRP is somewhat brittle, but if you consider if the FRP is somewhat well anchored, and the FRP rupture strain is about 1%, so that's significantly above the yielding of steel strength. So you do going to have some redistribution. And so I think it's possible, and we should include redistribution, even if it is a small amount. The other question is, was redistribution used in the original design? If the section was designed originally with moment redistribution, what is the impact on the retrofit? Then redistribution, if you consider redistribution from a strengthened region to a non-strengthened region, we should be able to consider maybe moment redistribution or vice versa. Or you have redistribution from strengthened into strengthened sections. So the research addressed all of these issues. But we cannot forget that according to the ACI 440, correct, there are limitations on our strength, how much strength you can actually put to the FRP on the section. But what I want to highlight to you is that what is the impact of not considering moment redistribution? There are many impacts, but I think it is important that I convey that to you before I go on with my presentation. Take a look at this curve. So that dashed line is the original design. So it was designed for that. You consider 20% moment redistribution in your original design, and that's your moment profile. Now let's imagine that the code does not allow moment redistribution, and let's say we want to increase the load capacity by 10%. The 10% is not from here that you would, for example, consider in a simply supporting design. So the increase in moment demand, moment capacity needs to go from this point to that point. So think about it. You're trying to increase the target load capacity 10%, but your moment increase capacity is 36%. Using ACI 440 strength limits, you cannot retrofit if you're trying to do this type of increase. Your FRP would actually have to be very high. So the question is, what if we allowed a redistribution somewhat of 75%? Now your increase is not 36 and 30%, and this might be within the strengthening limits. So in order for us to develop reliable, permissible moment redistribution limit, very similar to what we use in ACI 318, propel is that let's do some experimental, let's do advanced nonlinear finite element analysis, and let's see what we can propose. So this is a presentation overview. I'm going to show some of the overview of the experimental research program. We had done many beams, but I'm only going to show 3. The nonlinear finite element analysis, and then I will use these results to establish some permissibility moment redistribution limits. So this was the experimental setup. So you can see we're a 2-span, and we anchored the FRP with U-wraps, and this was quite intense, the wrapping of the FRP using U-wraps. And the reason for that, in some of the tests that we did not consider that the section, it doesn't matter if we consider moment redistribution on the section or not, the section will redistribute the moments. And we had shear failure on those beams that had low U-wraps. And so we had to increase on the second series of tests the U-wraps, and this is what we come up with. And this was the finite element analysis. So very similar, we use a finite element model that was try to replicate as much as possible our experimental setup. So this is, I'm only going to show you 3. One was the control unit. One was using a 6 inches wide strip at the top and the bottom. And I consider that as, let's call it low FRP. And for identification, I will say FRP-6, meaning the 6 inches wide FRP. And then we had the FRP-10 for 10 millimeters, and I call it high FRP. High FRP is within this context. And then the U-wrap. So in sections that we only had bottom FRP, we only use U-wraps. For sections that we had low, bottom and top FRP, then we use a continuous wrap just to make sure we anchor top and bottom. So this is finally showing you the experimental setup right before testing. And this was the Abacus finite element model. I will talk more about the supports. Actually, it was quite critical to model that accurately. Otherwise, our artificial confining the concrete in those areas was actually quite critical for the experimental results. So this is the Abacus finite element model. I'm only going to highlight a few things. So one is the supports. We use the 8-noded brick element, and we use a hyperelastic material simulation, which is what you would use for rubber. This was a low compressible rubber, and we actually were able to reduce a lot of those artificial confinement of the concrete in those areas. We had a host reinforced concrete beam, and we embedded the reinforcement bars. The reinforcing of the bars you see here was with truss elements given by this stress-strain relationship. And the concrete beam, we used the 8-noded brick element with the concrete damage plasticity. I will talk in the next slide more about these properties, how we derive those properties. But you can see here the dilation angle, it's 26. And the viscosity perimeter was not 0. I don't think in some cases it has to be 0. And it changed the duration, the time for simulation drastically. So that was, and we didn't compromise the experimental results. And this was then the CDP in compression and then the tension stiffening component of our modeling. And as you can see here is the embedded fibers for the steel. So this is how we derive the material properties. So we started with average test results from coupon tests. We put that in our finite element model. We did 100 simulations, compared the results, and we kept changing the material properties by doing simulations, and then we got this type of curve, and you don't see here, but that's the experimental results, and then we just use those properties that fit best the experimental results. You might say, well, I mean, yeah, you're getting very good results because you're doing all this work, but our goal was not necessarily to get exact experimental results, was also to be able to use this model with certain level of confidence to develop then our permissible moment redistribution limits. So now I'll talk about the FRP. Once again, we had top and bottom, and then these are the FRP sheets. So with a 4-noded shell element, we use the hunching damage parameters. The contact, we use the virtual crack closure technique with the fracture criterion, mixed mode behavior, some of those strain energies, and for the contact, going back to the original presentations, they might not control that one, but the model proposes that, requires that you enter those parameters, and the exponent was 2.05. We got very good results. I'll show some of this, and this then was all the material properties that we had to include. So for the FRP, we did use a fracture energy for the FRP damage evolution. So it's not a perfectly straight line after FRP fracture, and because otherwise you cannot duplicate or at least establish the post-failure of the FRP. The abacus just does not converge. So by using a FRP damage evolution, you do get post-fracture of your results. So that's something we observe. I agree. We need to be very careful of the mass density, and because we are using the concrete as our master surface with one mass density, but then what we found was that the mass density for FRP, because the program uses a master surface to a node interaction surface, it was quite critical not to have high stress concentrations if the mass density on the FRP is not small enough. So for us to be able to reduce some of those high stress intensities. And I think for the most part, the results were quite good. And as you can see, the beam, by the way, didn't have holes. We just put holes, removed some of those elements so you could see the internal reinforcement. And once again, this is how we derive at the material properties. We start with some simulations. We did, in this case, I'm showing here is 100 simulations. And then we pick the best simulations. You see the black one matches very well, I think, for the experimental results. So this is how we derive at the material properties. Well, one of the nice things about this program is, so I used abacus. So if I tell you that I had undergraduate students working on this project, you would say it's impossible. So I had a PhD student, and it was very nice. We use a graphical user interface. That means the undergraduate student is only inputting material properties, it's changing the beam. And actually in my senior design class, the undergraduate students were able to do quite a reasonable good result. And actually they end up going into the program and learning about abacus. What I was quite surprised, it will come back to me at the end of the day and say, you know, this and this, why are you doing this? And they didn't want to just blindly use the program, which I was quite surprised. I thought undergraduate students will do the thing and not wanting to know. And I was quite surprised at that exercise. That's why I'm showing you here. And so the program has the MATLAB code. The MATLAB code has script files. Then there's your Python that can be used into abacus for input. And then we had the Python for abacus output. So all of these results come in, and we never go into abacus, the CAE, the graphical interface with abacus. This was all done via MATLAB, and we wrote all these lines using MATLAB. And I think it is, in this case, proved to be quite a rewarding experience to see undergraduate students being involved and helping me to derive all those curves that I show you for material properties. So that was nice to see. So let's talk about going back to the presentation outline. So now I will show you some load deformation of our experimental results and the failure modes. So these are the experimental results. As you can see, I don't have much to talk about it because we are to show you some more exciting results. But we can say we have very good validation of our analytical model with our experimental result. I want to just show you the level 1 When I talk later about level 1 is when we had the first fracture of the FRP, level 2 when we had the second fracture, and then when, of course, we had that decline. I will show you some stress profiles for these 3 levels. This is the control unit, the low FRP and the high FRP, and very nice, you can see that unloading curve is very good, the post-failure. So the moment redistribution that I will use later, then that's why we needed to have very good experimental and analytical results, is then to compute the moment redistribution based on this equation. So here is some of the stresses, the RC beam and the FRP. Well, one of the first, so this is at the same level, displacement level, when we had first fracture of the FRP. So you can see the beam without FRP and with the U-wraps. As you can see, the shear stresses are very high, which would lead to failure of the beam. And I will show you the pictures next. And this is when we have the U-wraps. And as you can see, we have a significant reduction. It proves that the U-wraps did contribute to the performance of the beam. And this is given by the slope, so you can compare, so that we had just basically a failure, that we had some, these are the jacks, so we had some concrete spall in there crushing, and then the beam just had a shear failure starting from the top. And for the U-wraps, you see there was no failure basically of the section. The cracks remains pretty closed, and so we feel comfortable with what we are doing here. So let me show you now some strain profiles. So in order to develop some of our relations, what we did was that we looked into plotting moment redistribution limits, not just in terms of steel strain, but also in terms of the curvature ductility. In order to be able to get to this representation, we do need the plastic hinge length, and that's why it's in here. Since we have the strain profiles, let's look at different models for plastic hinge length, and let's see if we can compare this, so we can then use this equation to plot moment redistribution versus curvature ductility. And this expression was developed in an early work. So these are the strain profiles for the RO beam, so the control beam. And as you can see, the yielding of the steel is represented by the curve. This is where the load is. So you see the distance between there and there, of course, is not the same as there and there because of your shear span ratio. So the shear span ratio is here, and the shear span ratio is not from here to there, but is from here to about that point. So you can see is going to have an impact on the plastic hinge length for these structures. So let me show you then some interface concrete to FRP contact stresses. So this was analysis we did without U-wraps. So you start to have some contact stresses very high there. You increase, you start to see basically some spread, and then look what happened. It doesn't fracture. You start to have delamination at that end. Okay, so it was nice to see that actually the model was duplicating what I had expected. And some of the beams that we didn't have U-wraps, this is exactly what we observe, okay? And then you see when we put U-wraps, very nice, very low contact stresses, except in some areas there, I don't know if you can see, but we had some contact stresses there. But we didn't have any pilling or debonding of the FRP. It was a sound and a very good procedure until, of course, we had fracture of the FRP. So these are some stresses at level 1. So we had fracture of the FRP. Then level 2, we had, so the FRP has already fractured. We start having fracture at the top, and then basically the FRP is no longer doing anything. That's why the beam with FRP post this level just went back to the curve with the control unit, and that makes sense. And this is then the failure on the bottom there for the FRP. And these are the strain profiles then. These are the reinforcing strain profiles. So the spread of plasticity, so you see, is very close to what these lines were from the control unit. So these are the strain profiles on the longitudinal FRP sheets. And as you can see, the bottom FRP, the strains were much higher than that one. I wish I had done this analysis before, because I would like to see the reverse, but sometimes you need experimental results to calibrate. By the time you run out of funds, and then you cannot redo more tests. Hopefully I'll get to do that in the second round of tests. And this is for the high FRP, and once again we got the same results, although the differences between that point and that point for the high FRP is not as high. So different plastic hinge link models have been proposed since 1956 until 1992 by Pauli, Priestley, and Park. Remember that these recently were done for axial loaded concrete members, columns, where these were for beams. So let's compare those results. So based on this was all analytical. So condensing all the results, plotting some averages. So you can see the Baker, 1 means is good. So the Baker did very well. So did the Maddock. And look at those columns, plastic hinge link models didn't do very well. So I think that this shows that we need to be very careful using these models for the plastic hinge link. Now we wanted to have a very good confidence that the plastic hinge model we are using is reliable, so we can then plot momentary distribution limits versus curvature ductility. So very quick, some momentary distribution limits. I'm almost done. So using this equation from a previous study, and the momentary distribution experimentally for the control beam was 17, but take a look at the FRP retrofitted, it was not 0. So we have very high redistribution limits. So even if we do not consider in design redistribution, we will have redistribution in the FRP retrofitted structure. So it's very critical that we understand and ask the question, what does this mean in terms of performance? Will it affect the shear design of the beams? Because you have a shift in the bending moment diagram. As we know, then that increases the shear, and that's quite significant. I'm not going to show that results here. And so these are the ACI permissible for regular reinforced concrete. So top and bottom FRP, we use very different ratios, and this is basically when we have an F0, no FRP there, only at the bottom, and then we vary the reinforcement that you see all those points, but take a look, you cannot see anything. The steel strain means the steel strain is controlled by the FRP, okay, and the FRP is 0.1, which is here, but we have higher steel strains in the steel when we have, so we cannot really plot this versus steel strains. Is a little bit better, and we tend to separate our results when we use this in terms of curvature ductility. So we have one limit that we can clearly observe for about 3, the momentary distribution limit could be somewhere around this level. These curves were basically average results from all of the simulations we have did that we plotted these redistribution limits. And then for these regions, so we could say maybe something higher. And so that's the analysis that we use to be able to provide some permissible momentary distribution limits. Another thing that we need to consider, and I'm not going to show you here in very detail, but I want to alert, is then the strengthening limits given by that expression by ACI 440. And there are some sections, so it means the section does not meet that criteria limit, so we cannot retrofit for those levels. But you see, look how many configurations of retrofit actually met the criteria. So I would say for most of the sections we should be considering momentary distribution limits. And so these are some conclusions from our work. For ductility, curvature ductility of 3, considering 7.5 seems reasonable, and for higher levels, these are some other ones. Limits, certainly in terms of ACI 318 redistribution limits and the strengthening limits by ACI 440. I want to acknowledge some of the work of my co-authors, my graduate student, Raminder K. Singh, and my co-author on this work, Timothy Ibell from the University of Bath in the UK. Thank you for your time.
Great, thank you, Pedro. We can take a couple of questions. We're just about at the time. Jimmy?
Thanks for our last presentations. Quick question about the moment distribution equation, which is a function of Py and U, this kind of things.
This one? Oh, the other one. Yeah.
Simplest one. Things are kind of so about the background and sources given publications and so on.
So the momentary distribution is 1 minus the momentary distribution at, so it's a function of your moment at the limit versus the yield moment. So if you work out, we have this expression developed in an early paper. So if you expand the expression, that's how we got to this relation. Yes. It's a very long derivation, but using those results, and that's how we have derived. I can show you, afterwards, and the derivation. Yes.
We can take one more question.
Pedro, a lot of great data here. It's wonderful to see that. I noticed that in the beams that you tested, you did use a lot of URAP anchors. And I kind of lost a little bit the train of thought about, did you have any conclusions about if you had a beam with longitudinal FRP, I know URAP anchors, what would be the moment redistribution for that beam versus one that you tested that had significant URAP anchors, therefore you were able to reach the tensile strength of the longitudinal FRP?
The debonding occurs within the elastic region, so way before the point of 1. So the still yields, but and plus momentary distribution, you have to have a very good reliability of the ultimate failure, which you will not have it if you don't put the URAPs. So we did that test, and I was very surprised to see basically the lamination for continuous beams towards the end of the bottom FRP, close to the middle support. Okay, because there's a very high shear ratio there in that zone.
So for future maybe design guidelines, if you want to take advantage of moment redistribution with FRP, you need to make sure that you anchor it.
So in the new recommendations of ACI 442, we actually specify that if you are to consider momentary distribution, you do need to anchor the FRP. So that was how we addressed that concern, and I agree with you.
Okay,
Even continuation to this discussion, in the past we did several tests, experimental tests, also numerical work, similar to this, but using slabs. Because in beams it's more difficult in reality. It is quite difficult to have in reality continuous beams and strength, because we have the columns, it creates a lot of problems in the case of frames. We have columns and beams, and to achieve continuity in the arching region is not simple. And in case of slabs, it's quite common. So slabs are often beams, and then we, as I have faced even this situation in real practice, and in this case we use the NACM, linear surface modeling. And I do not face any problem in terms of the quality. So if we only what happens is that when we want to increase significantly load carrying capacity, and then we need to introduce in the arching region a significant number of NACM laminates. In this case, we can have the rip-off. But congratulations, Pedro, because, well, in fact, even in the slabs, we found moment distribution of 30%.
Yeah.
What is very important now with this very nice work is to explore or to verify the influence of the equivalent reinforcement ratio. What is equivalent? Is to consider the existing steel bars plus the FRP that we introduced. And you will realize from this pragmatic study that we did for the slabs with MSM that the moment distribution is very sensible to this ratio that you apply in the sensing region or in the housing region. And this is quite important. Congratulations, very nice. I'm very happy to verify that, in fact, we can have moment distribution even using FRP.
Okay, thank you.